This lesson is an introduction to exponential functions and graphs. And we haven't looked at any functions that look like this yet all semester. All of the functions that we've looked at so far this semester have been polynomials or roots of polynomials or rational functions, which is one polynomial divided by another polynomial. So if I have a polynomial, I'm going to have my x, my variable, as my base, and then have a square on it, or to the first power, or a constant, which is actually x to the 0 power. But the x is the base, and the exponent is fixed. This is a polynomial. And what we're going to look at starting with this lesson is if we have some other number, a, and then the x is the exponent. So the base, a, has to be some number that's positive and not equal to 1. And we'll see why that is in just a few minutes. So the x is the exponent. And that's why that's called an exponential function. Hopefully you've just finished looking at the exponent review and you understand how exponents work, even if they're negative exponents or fractional exponents or irrational exponents. So let's say that we have the function f of x is equal to 2 to the x power. And what we're going to do is we're going to graph 2 to the x power. I'm going to give you a bunch of x's. You're going to figure out what y is, what your output is. You're going to plot all of those, and then you're going to graph them on a coordinate system. And I want you to make your coordinate system fairly large. Make it about at least a quarter of a page to a half of a page, because we're going to use that function. We're going to look at it, look at characteristics of it, and then we're going to figure out what about that function, that graph, would remain the same even if our base changed, and what would remain the same. And then we're going to come up with a quick and easy way to graph exponential functions without having to plot a whole bunch of points. So what we're about to do is an exercise in learning about exponential functions, but it's not how in the future we are going to graph exponential functions. So you don't have to worry about knowing what values of x to plug in. So what I want you to do is take each of these numbers plug them into the function and figure out what y is. I'll do the first one so you can see what I'm saying here. So if x is 3, we're finding f of 3, which is 2 to the third power, which is 2 times 2 times 2, which is 8. So we have 3 is our input, 8 is our output, and we have the ordered pair 3, 8. I want you to go ahead and do the same thing with each of the remaining numbers, the 2, the 1, the 0, etc. And again, if you need a review on how negative and 0 exponents work, watch the video, the exponent review video. So pause your video, find each of these ordered pairs, and then plot each of those ordered pairs on a fairly large coordinate system. And when you've done that, turn the video back on. Okay, so we have 2 squared is 4, 2 to the first power is 2, 2 to the 0 power is 1, 2 to the negative 1 power is 1 over 2, which is 1/2, 2 to the negative 2 power is 1 over 2 squared, which is 1/4, and 2 to the negative 3 is 1 over 2 cubed, which is 1/8. So we have the ordered pairs, 3, 8, 2, 4, 1, 2, 0, 1, negative 1, 1/2, negative 2, 1/4, and negative 3, 1/8. And I plot each of those on my coordinate system. These are my x's. And my y's. So I plot each of these, 3, 8. And I'm doing this rapidly because hopefully you turned your video off and did this yourself, and you were just looking at my work to check your own. And as I go out here, I'm just kind of eyeballing 1/4, 1/2, 1/8. And I see that I'm getting closer and closer and closer to the x-axis, but I'm not ever going to actually cross over. If I went out here to negative 4, I would have 1 over 2 to the 4th power, which is 1/16, and so on. And they're getting closer and closer and closer here. And as I come out to 4 and 5 and so on, my ordered pairs are going to get higher and higher over here. Now, so far, I just have a finite number of ordered pairs. But let's think about if we can actually have a point other than in between these ordered pairs. So, for instance, let's say I went out here to 1/2. Can I have my base is 2. So can I have 2 to the 1/2 power? And in our exponent review, we saw that that was the square root of 2. There is no number that can multiply by itself twice to get 2, but the number square root of 2 does exist. It's an irrational number, and if you plug that in on your calculator and do second square root 2, enter, you see that you have a number that keeps going forever, an irrational number. So I use the approximately equal to symbol 1.41. And if I come over here on my graph and come up to about 1.41, I see that I have a point on the graph in between those other 2 points. And I can do that infinitely many times and actually fill the graph completely out and come along that way and then keep going up in that direction. So I can find infinitely many points and fill in every single ordered pair on this graph. For instance, if I went out here to the number pi, and remember pi is approximately equal to 3.14, etc. So it's out here a little bit past 3. And if I came up on my graph, if I guessed what that would be equal to, and I don't think I'm drawing this very well, but if I actually did 2 to the pi power on my calculator, and I can do 2 caret on my calculator, pi, and that's equal to 8.8 point something. So I see that I come over here to my graph and I'm at about 8.8. So we have infinitely many points going up forever and going back in this direction. So this is the graph of f of x equals 2 to the x power. And what we're going to see is that regardless of what my base is, as long as it is a positive number, as long as a is a positive number greater than 0 and a is not equal to 1, we're going to have a graph that looks similar to this. Now, it can't be equal to 1 because if I took a to the first power, if I took 1 squared, 1 cubed, 1 to the 50th, that's always equal to 1. And that is not an exponential graph. That's just the line y equals 1, which is the horizontal line. So that's why it can't be equal to 1. So let's look at some characteristics of this graph right here that are going to be true regardless of what my base is. But before we do that, let's write what our domain is and what our range is. So pause the video for a moment, look at the picture, write the domain, and write the range, and then turn the video back on. And we see that if we sweep across from left to right, our domain is negative infinity to infinity. And that tells me that I can use any value for x that I want. Negative, positive, 0, rational, irrational. I can use any exponent I want. And my range, notice my range is starting here at the x-axis, which is y equals 0. But I'm not ever actually crossing that axis, and I'm not reaching that axis. So that means that y has to be greater than 0, getting infinitely close to 0, and going to infinity. All right, what I want you to do is look at this graph and think about things on this graph that are going to be the same regardless of what my base is. See if you can write those down. Just jot down a few things. Think about it, jot it down, and then we'll compare. Okay. Hopefully you did what I asked and you wrote down some things that are going to be the same about this graph regardless of what the base is. And you might have noticed that the general shape of the graph is going to be the same. We're going to have that curve, which is called an exponential curve, regardless of whether the base is 2 or 3 or 4 or 5, etc. And hopefully you noticed that anything, any positive number to the 0 power is going to equal 1. So we're always going to have the point right here, 0, 1. We're also going to have that behavior over here on the left where the graph is coming down and getting closer and closer and closer to that axis, but not ever crossing it. And remember, that's what we call an asymptote. So we see here that we have a horizontal asymptote at the line y equals 0. And notice that this asymptote doesn't have anything to do with the asymptotes that we learned about with rational functions. I mentioned at that point that the asymptotic behavior is the name of the behavior, but it occurs for many different reasons. And we're also going to see that the graph is going to curve upwards like this. And if I go out here to the x equals 1, we're at a, because a to the first power is equal to a. And if I come back in this direction, we're at 1 over a, because a to the negative 1 is 1 over a. And we also see that our domain will always be negative infinity to positive infinity, and our range will always be 0 to infinity. So those are some things that we know will always be true. The domain, the range, the general shape, the horizontal asymptote, and the ordered pair 0, 1. The things that will be different, depending on A, are going to be the a to the first equals a, which tells us how steeply we go up on this side, and the a negative 1 equals 1 over a, which tells us how quickly we come down on this side. So this is going to be our model for graphing exponential functions from here on out. In our next lesson, we're going to graph a few exponential functions using this method, and we're going to use transformations to see how we can find a little bit more complicated one using our transformation rules.